Hello friend, good morning. This is Abhishek Kumar, and in the last discussion we talked about how to analyze the indeterminate structures. Dear friends, while analyzing the indeterminate structure, we use principle of superposition in which we draw two types of bending moment diagram. One is the free BMD, means free bending moment diagram, means assuming the beam as simply supported beam we draw bending moment diagram, and after all we draw fixed end moment diagram. For it we should be known fixed end moment. So friends, we remembered some standard case of fixed end moment diagram. Let us talk about those cases. Let us see. Dear friends, let us revise the previous discussion. We studied the simply supported BMD. Just at a glance we can see that if this is a simply supported beam carrying point load at mid span, this distance is L by 2, this distance is L by 2, we can draw its BMD as this. This will be like this. It is the simply supported bending moment diagram. Plus means sagging. Plus means the compression in reference face. Reference face is top face, means compression means the shape of beam will be like this, right? Second case was this. If simply supported beam carries a UDL, means assume it as a thread and the deflection of thread and put some soil over it, it will treat as simply as a UDL, and the shape of the thread will be like this. Now BMD will be like this. Invert this shape, BMD will be like this. Maximum bending moment will be at mid span and its value will be WL square by 8. This is L by 2, this is L by 2, right? Third case was if case is like this. For example, this is load P1, this is load P2. For example, this distance is x1, this distance is x2, and this distance is x3. Now let us we can calculate, this is A, this is B, we can calculate RA, we can calculate RB. In order to draw BMD, I told you that at this point bending moment will be 0, here also bending moment will be 0, and at these 2 points we can calculate. For example, here bending moment is RA into x3, and let us suppose here bending moment will be RB into x1. Now join them linearly. This will be the bending moment diagram of this structure. This is okay. So in this manner we can draw simply supported BMD of any structure. If it is carrying a couple, this is a couple, and like this, this is M, this distance is A, this distance is B. I told you that directly you can learn that at this point here bending moment will be 0, here also bending moment will be 0. So we can calculate bending moment at this section, and I told you that bending moment will be, how will you calculate? This arrow hits the beam at bottom, means opposite to the reference. Upper face is assumed as reference face, so it hits the beam at bottom, means opposite to reference face, means negative. Negative means plot here, and on this beam it hits the beam on top face, so positive like this. So it will be plus, it will be minus, and value will be at A distance it will be MA by L, on B distance it will be MB by L. So we can draw the BMD of this, and some standard, some special case was also there like this. We can draw its BMD. BMD will be it will be the deflected shape of thread, inverted, it will be the shape of bending moment diagram. This is the plus, and this value will be WL square upon 9 root 3, and this was L upon root 3, and the overall was L, right? So these were some standard cases which we should be remembered always. One more case was there like this. This was the case. The thread will symmetrically deflect, so this will be the BMD. Bending moment will be maximum at center and will be given as WL square divided by 12. It will be the BMD. Okay, so in this manner we can draw BMD. Now we can also draw fixed end moment diagram. If this is the simply supported beam, this is the fixed beam and it carries P load at center, so fixed end moments were these two, and value was PL divided by 8, PL divided, here was PL by 4, add 4, so it will be PL divided by 8. If this is the simply supported, this is the UDL carried by fixed beam, value was WL square by 12, WL square by 12. And the next case was like this. This is the case. This is W. This value was WL square by 30. This value was WL square by 20. Next case was this. So these are the result we should be remembered directly. This was 5 upon I think 94, 5 upon 96 WL square and 5 upon 96 WL square. And if it is M moment at center, this is L by 2, this is L by 2. The couple will be, these end moments will be in same direction, and value will be M by 4 and value will be M by 4. So these are some standard result we should be known. Now how we can draw BMD? Listen friends, while drawing BMD I told you that we use the approach that is called as principle of superposition. For example, this is the case. Let us take the some numerical example. Let us take the numerical example. For example, this is a beam. This is a beam carrying a load of 36, let us suppose 36 kilonewton. This is 2 meter, this is 4 meter. Now he asks draw BMD. This is A point, this is B point, and this is the C point. We can draw BMD. While drawing BMD, first of all we should be known the fixed end moment, means draw its FBD. Its FBD will be like this. At this section shear force, and this will be bending moment, and this will be bending moment, and this is 36, and this is 2 meter, this is 4 meter. The answer will be the bending, this couple, this bending moment will be M A B square divided by L square, means 36 into 2 into 4 square divided by 6 square, and the answer will be 36 into 2 into 4 square divided by 6 square. This answer will be 32. Similarly, we can calculate 36 into 2 square into 4 divided by 6 square, and this answer will be 16. So we can say that this beam can be written like this. Earlier it was fixed beam, but here we can calculate. We have already calculated the end moments. One is 13, one is 62, and one is 16. 32 and 16. Now this is A, this is B. We will draw the BMD of this beam using principle of superposition. How principle of superposition? We will draw two diagrams. First will be like this. First will be called as simply supported diagram, means this is 36, this is 2 meter and this is 4 meter. So its BMD will be like this, and ordinate, this is the plus, and this value, this height will be PAB by L, means 36 into 2 into 4 divided by 6. This value will be 48. This height will be 48. Now we can draw the simply supported BMD, means this is the simply supported beam, this is 32 and this is 16. So I told you that both the arrow hits the opposite to the reference face, means both bending moments are negative, and negative bending moments are plotted below the line. But in case of, since we have to superimpose over it, so later on we will have to change the sign, means we now can plot this is 32. 32 means it is hitting the opposite to the reference, means negative, and negative will be plotted up. Negative will be plotted up. This is 32. This is 16, again negative. So negative will be plotted up. Means we can learn that in order to superimpose two areas, the positive of first diagram will be plotted up and negative of first diagram will be plotted up. Means one's positive will be plotted up and one's other's positive will be plotted down. Then only we can superimpose two areas. See how. Now we are needed to calculate the value at this, means 2 meter. This is the 2 meter, this is 4 meter. Means we should know this value. This is 2 meter and this is 4 meter. How we can calculate? We can calculate as this. This is 16, this is 32. So we can draw the bigger figure like this. This is 16 and this is 16, this is again 16, total was 32, 32 minus 16, 16. We want to calculate this value. This value will be 16 plus this value, and this value can be calculated as, this is 4 meter. You can say that this line on moving 6 meter, the height is 16. So on moving 1 meter, height is 16 by 6. On moving 4 meter, height will be like this. So we can say that the total value is the total ordinate, this here to here, will be 16 plus 16 by 6 plus 4, and this is 10.67. So the total height. Now draw its BMD. See how. So this is this height is 48. This height is 48. This is 48. Now this is 32, means this is 32 and this is 16. Now add 2 like this. See, this was minus and this was plus. So this was plus and this was minus. This area is cancelled. It will be minus. It will also be minus and it will be plus. Now this ordinate will be, this ordinate total was 48 minus, and this was 16 plus 10.67, means 26.67. So this ordinate will be 48 minus 20, it will be 21.23. So dear friends, this is the bending moment diagram. Our aim will be to calculate the bending moment diagram and the maximum bending moment at certain locations where we can calculate. So this is the procedure how we can draw BMD. Right, next how to draw BMD. Let us suppose one more example. Example is like this. This is the example. He asks you draw BMD of this beam. This is 16, this is 2 meter, this is 2 meter, this is A, this is B. So dear friends, our first aim is to calculate these end moments. What is the formula? If m moment is at midway, so the answer will be m by 4, means 16 by 4 means 4, and the direction will be in the same direction, means both will be clock. So we can plot that. We can draw like this, shear force, and this will be the direction clock, and this will also be clock, and this is the 16, 2 meter and 2 meter, this is 4 and this is 4. Now draw BMD. Friends, draw BMD. Look, first of all we will draw simply supported BMD, means assuming the beam as simply supported beam. This is simply supported beam, this is carries 16 moment, this is 2 meter, this is 2 meter. I told you how we can directly draw BMD. Here will be 0, here will be 0. This arrow will hit at bottom to left beam and will hit top to right beam, means for left beam bending moment will be minus, so it will be minus will be plotted down, and for this beam it will be plus, like this. This is plus and this is minus. This height is m into 2 by L, means m means 16 into 2 by L, L means 4, so it will be 8 and it will also be 8. This will be MA by L. So 8 is this and 8 is this. Now now draw the end moment diagram. Assuming the beam is simply supported, this is 4 clock and this is also 4 clock. One arrow hits up, means to the reference face, other arrow hits to the opposite to the reference face. So how will we draw? Here look, this arrow hit to the reference face means plus should be plotted up, but for this diagram we will plot plus down because we want to superimpose over it. So it is 4 and it hits down, means negative, or negative should be plotted up. This is 4 and it will be like this. This is plus and this is minus. Now superimpose these two, put it over it. This is also mid and this is also mid. So how, see how we will put it over it. This was this and plus, this is plus, this value is 8 and this is 4, means it will be here. This is also 4, like this. Now this will also pass. See, this was minus and this was plus. This zone cancelled, plus cancels minus, so it remains plus, and this was minus, it is cancelled, so this is minus. This was plus and this was minus, this is cancelled, so this is minus and this is plus. This is the final BMD. This value is also 8. How to draw its deflected shape? I told you plus means compression in reference face. So plus means like this, compression in reference face. Reference means upper face, from here to here, tension in reference phase, beam will bend like this, here to here compression in reference phase, here to here tension in reference phase. So its shape will be like this. Since it is the fixed beam, and fixed beam never bend like this, but in order to generate the same effect, we can beam bend like this. It is also giving tension at toe face, and it is also giving tension at toe face, but it is not possible because it is fixed and here will be straight. So beam will be like this. From here to here, this is point of contraflexor O1, this is point of contraflexor O2, this is point of contraflexor O3, right? So 3 point of contraflexor. Look how from here to here like this, from here to here like this, and from here to here it will be like this, and sorry, it is wrong. It is like this. This means like this. So from here to here it will be like this, and from here to here it will be like this. Now it will be, since the beam is symmetrical, here to here you will see that like this and like this. This is the deflected shape. See, this follows this, it follows this, this follows this, and this follows this, right? It will be the deflected shape. In this manner we can draw bending moment diagram of a structure. Now friends, what is our aim? This was the bending moment diagram. If supports are only 2, means there is single span, but if spans are more than 2, what will we do? How will we calculate? So in that manner we follows stiffness method. What is the stiffness method? We use stiffness of the structure. What is stiffness? Dear friends, stiffness is the moment required to produce unit rotation or unit displacement. Means moment required stiffness of a member at a joint. Stiffness is always calculated of a member at a joint. For example, we should be learned some formulae like this. These are the discussions of strength of material in deflection of beam. If this is a simply supported beam, carries m moment, right? It carries m moment. So how can you calculate the deflections? See how. You will say that it will bend like this. It will bend like because it is pressing it down. So it will bend like this. This is end A, this is end B. This slope theta A will be ml upon 3 EI, and this theta V will be half, means ml upon 6 EI. You should be remember this formula. Now next formula is, if I make it fix here and now I apply again the same moment m. See what is the difference? The deflected shape of this, it will like try to bend like this, but here is fixed. It will not permit it to bend like freely, and it will ask it to make slope here 0. So from here to here will be like this, and from here to here it will follow its shape. This will be point of inflection. These are point of inflection where bending moment, this is the point of contraflexor. Contraflexor means where bending moment changes its sign. Same points are reflected in the beam are called as point of inflection. Significance of point of inflection is that at point of inflection beam changes its curvature. Curvature means here is sagging, this is sagging, this is hogging, this is sagging, this is hogging, right? So the deflected shape of probe cantilever beam will be like this. Now you tell me please, this is theta A. Will this theta A will be more or this theta A will be more? We are applying same moment. If we are applying same moment, and in order to generate this figure, the answer in this case will be ml upon 3ei. Now generate this figure, I will have to press it like this. This means we will have to we will have to apply a moment in this direction, means this theta will reduce. If I will press it, this theta will reduce, and reduce means this denominator will increase. So we can learn value theta as ml upon 4ei. ml upon 4ei. We should be learned this value, ml upon 4ei. Now friends, what is the stiffness? Stiffness is, remember, stiffness of member AB at joint A will be the moment required to produce unit displacement. Means to produce theta displacement we require m moment, but if we want to produce unit displacement, means if theta equal to 1, then m equal to k. M equal to k means stiffness of member AB at joint A, and m will be equal to, theta will be 1, 3ei divided by L. M equal to KAB equal to 3ei divided by L. In this case, if I want to calculate the stiffness of joint member AB at joint A, it will be put theta A equal to 1 and the m will be KAB. So m equal to KAB will be ml upon 4ei, 4ei divided by L. So you can see that this stiffness is more, this stiffness is less. Dear friends, remember one thing, that the stiffness depends upon far end. This is the near end, means end at which you are applying moment, and this is the far end. If far end is hinge, means stiffness will be less. If far end is fixed, stiffness will be more. 4ei divided by L, stiffness will be more. So this is the concept of stiffness. Far end is hinge, far end is fixed. Now one or two things are also important. Look how, if I want to calculate this you are applying m moment, and if I want to calculate how much is the reaction, see here, you should be known one or two formulae like this. If this is a simply supported beam, it carries point load P, so its deflection will be here, it will be PL cube upon 3ei. Now if it is the cantilever beam carrying m moment here, again the deflection will be in the direction of moment, and the answer will be ml square upon 2ei. Right, so these two results should be known. Now look, this is a probe cantilever beam. This is probe cantilever beam. One person asked me calculate, this, he applies m moment at end A, this is end B. So he asked me calculate end moment, means we have to analyze this beam, but the analysis is not possible using equilibrium equation because unknowns are 1 is here and 3 are here, but equilibrium equations are 3, means 1 is extra, so we should use compatibility equation. Let us suppose this is RA. Now you can use principle of superposition. How? You can say that this is the beam and this is M and this is RA. I can say that, let us suppose for example this is M, this is M, right, and I can also take at this is R. Principle of superposition, it says the beam will deflect like this, and it says beam will deflect like this, but ultimately beam is not deflecting because this is hinge joint, so net deflection of this equal to this. Okay, this deflection equal to this means net deflection should be equal, or had this been like this, for example, had it been like this is M moment, let us suppose this is the RA reaction. Now we say that this is M and this is RA. We can say that this will deflect like this will deflect like this, but the net deflection of this joint is 0. This is called as method of consistent deformation. Means here net deflection is 0, so we can calculate this deflection as ml square upon 2ei, and we can calculate this deflection as pl cube ra l cube upon 3ei, and the net deflection is 0 means this up deflection equal to this down deflection, or this minus this equal to 0. So we can say that ml square upon 2ei equal to ral cube upon 3ei. So from this we can calculate ra equal to 3m divided by 2l. Now using this RA we can calculate this MA. For example, this is MA. Calculate this MA. So now since RA is known, RA equal to 3m divided by 2l. This is A. This is B. So this is MB. We can use summation of MB equal to 0. Means about this point one reaction will here. So you can say that RA means 3m upon 2l into L will rotate like this and equal to M plus MB. So MB will be, this L is cancel, 3m by 2 minus M means M by 2. Means this case should be remembered, this is expected to be remembered from you, that if I apply M moment at this end and if far end is fixed, means half moment will be transferred here. You see na, MB equal to M by 2 means this is M by 2. So if you apply M moment at near end and if far end is fixed, half moment will be transferred at this end, fixed end, right? And this is the condition of beam is prismatic, because the beam is of same cross section EI and there is no internal hinge, means curvature is not broken, then only we can say that. But if far end is hinge, if far end is also hinge, and then I will apply M moment, so it will bend like this, it will bend like this, so there will no moment transfer here, means here will be slope but no moment will be transferred. So we can say that if I want to calculate carry over factor, COF, carry over factor means carry over moment upon applied moment. We applied moment M, and how much is carry over means how much is transferred, this is M by 2. So carry over factor is half, carry over factor is half. But if beam is not prismatic, for example, this is the case like this, this is L by 2, this is L by 2, it is EI and it is 2EI, and I apply M moment here, half should be transferred here, half should have been transferred here, but a half will not transfer. Since this member is stronger, means more than half will be transferred, means this value is greater than half, so carry over factor will be greater than half. In the similar case, if it is just opposite like this, this is 2EI and this is EI, Now I transfer m, so half should have been transferred here, but it will not be half, it will be less than half. More moment will be taken by the heavier member and smaller will be this, so carryover factor will be less than half. Sometime he ask you question, this is the question, this is internal hinge, this point is A, this point is B. He asks calculate carry over moment, calculate carry over moment, this is M, so how much moment will carry over? Means simply analyze the beam and calculate MA. For example, this is B, so it is MB. Here at A I have applied M. So in order to calculate M beam in general equilibrium equations, it is determinate beam, because the total unknown are 1, 2, 3, 4 and equilibrium equations are 3 plus one more equation is that it is internal hinge and as bending moment at this will be 0. So we can calculate first equation, bending moment at C equal to 0, means let us suppose this is RA, this is RA, so you can say that RA into A in this direction equal to M, so RA will be M divided by A. Now we can calculate this. Now we can see that summation of moment about B should be 0. One reaction will be like this, means summation of moment means force rotating in this direction means RA M divided by A into A plus B L, and this is this, it will rotate like this, and these two will this means M plus MB, hence MB will be M, it will be M divided by A. Okay, M divided by means ML upon A minus M. Now if you take LCM, L means A plus B minus MA divided by A, it will be cancelled, it will be MB divided by A, so it is MB. MB means this much moment is transferred here. So if I want to calculate carryover factor means transferred MB upon applied, so it will be MB divided by A upon M, so it will be B divided by A. This is the carryover factor, right? Now we come back to our concept stiffness. What is the meaning of stiffness? Dear friends, look here. For example, now the question will be like this. So far we have drawn the BMD of single span, and in this single span we have remembered the value of fixed end moment of standard cases. For example, it is P load, so fixed end moment will be like this, and simply supported we can easily draw. But if question is like this, this is the question, this is beam, fix, and this is intermediate support. Remember friends, we are talking about the rigid jointed structures. Structures are of two types. One is pin jointed structure, for example trusses, and one is the rigid jointed structure, means joints are rigid, means welded. There is no broken, member is not broken here, it only supports here, right? So it is a continuous beam, and here is intermediate support. Now its bending will be like this. Remember one thing, if I applied load here, means this span will go down, this span will go up, and since this is fixed, so it will be like this, and like this, it is fixed, right? So this angle, this joint B, this beam will remain straight here, because earlier it was straight, so after deformation or after loading it will remain straight at this joint B. So I will say that this is theta B, this will also be theta B, right? So this is the behavior of the structures, means either beam can bend like this, or for example if you apply load here, beam would like this. So now this was theta B, and this was theta b, right? So this will be where this is the rigid joint, means earlier it was straight, so after loading will also be straight. So this is the way. Now if we want to analyze this structure, since remember friends, it is not hinged but it is not also fixed, so it is the partially fixed, means it is partially fixed means had it been completely fixed. For example, I take a question like this, right? This was loading 2 meter and this is 12 kilonewton per meter, this is 4 meter. Dear friends, see, you see that how to analyze the structure, since this joint is not fixed, but had this joint been fixed, let us assume this joint as fixed and this is also fixed. This is A, this is B, this is B, this is C. So now we could calculate 2 meter, 2 meter. These fixed end moments. Fixed end moment was PL divided by 8. PL divided by 8 means 4. It will also be 4. Now it will be WL square divided by 12. WL square divided by 12 means it is 16 and it is also 16. Dear friends, we could draw. Now we can draw BMD. How? One will be simply supported BMD, this is point load like this, and one will be end moment. Both arrow hits down, down means negative, negative will be plotted up, negative will be plotted up. So it will be its diagram, minus, minus, plus. Similarly we can draw this, it will be parabolic and both arrow hit down, negative, negative will be plotted up. So it will be 16, it is 16, this is plus, this is minus, this is minus. This would be the answer. But dear friends, remember one thing, that this joint, since there is no external moment at this joint, hence this joint should be in equilibrium. Equilibrium means net clockwise moment equal to, and equilibrium condition of equilibrium is clock equal to anti-clock. At this joint, this is saying that at this joint clock is plus 4. Clock means our sign convention will be clockwise moment will be taken as positive and anti-clockwise will be taken as negative. So let us take this joint B. So this joint B, you will say that this is saying that MBA is clock means plus 4, and this is saying that MBC is minus 16. But at this joint B, since there is no external moment and internal should also be balanced, so their summation should be 0, but their summation is minus 12. Minus 16 plus 4, summation is minus 12. So we cannot solve like this. Dear friends, what should we do in this manner? We will say that one person called Hardy Cross gave the method of stiffness. He asked that this is unbalanced. This unbalanced moment is minus 12. So you apply plus 12 bending moment. Here you apply plus 12, and after applying plus 12, this is minus, minus means anti-clock, so you apply clock means plus 12. Plus 12, as soon as you will apply plus 12, this minus 12 and plus 12 will be 0, so this joint will be balanced. But as soon as you will apply plus 12 at this joint you will plus 12, sum of moment will be taken by this member and sum will be taken by this member, and if far end is fixed, half of this moment will be transferred here and half will be transferred here. This is the concept. But how much will be taken by this means, you will say that you will draw like this. See, this is here is plus 4 and here is minus 16. Their summation is minus 12. Apply plus 12. Now plus 12 means clock. You are applying plus 12 moment, but how much should be given at this and how much should be given to this. Dear friends, how much should be given, it will be decided by the stiffness. Which member is more stiff will take more moment, and is less stiff will take less moment. For example, in this case you will see that since far end is fixed, so stiffness of this member BA, KBA can be calculated as 4EI divided by L, means 4EI divided by 4, this is EI, and KBC again far end is fixed, 4EI divided by 4, this is also fixed, means both are equally strong, so moment will be distributed half. So this is minus 12 unbalanced, apply plus 12, and half will be given, plus 6 here and plus 6 here. Here what was the condition? This was 4 and it was anti-clock, means it was minus 4, and it was 16 means clock, means it was plus 16. Now you will say that half of, if you are applying some moment here 6, so half will be transferred here in the same direction, understand? And here also you are applying plus, means clock 6, so half will be transferred in this direction. So you will say that its half will be transferred, means it will be plus 3, and it half means plus 3. So final end moments will be minus 4 plus 3, means minus 1, 6 plus, this will be 10, and minus 10, and it will be 19. Now you can say that M A to B is minus 1, M B to A is plus 10, M B to C is minus 10, and M C to B is plus 19. Okay, so now we can draw B and D, we will see later. Dear friends, look one more thing. This was called as balancing principle. See one more thing. For example, this is the beam, this is the beam, this is the intermediate support, its EI is EI, length is 2 meter, its EI is 4 EI, and length is 3 meter. Now there is no loading, but this is A, this is B, this is C. I apply a moment of 9 kilonewton meter at joint C. Now he asked draw BMD, calculate end moment at A, end moment at B, or analyze the beam. How will we calculate? See this, if I am applying any moment at a rigid joint, so see this is beam, this is a rigid joint, I am applying M moment here, so half will be transferred here, and in the same direction, this was clock, it is also clock, M by 2. If I am applying M moment at this end, but it is hinge, so no moment will be transferred here. But dear friends, if at a joint there are, this was the condition of one member at a joint. If this joint there was only one member, and if I apply M external moment at this joint, means this entire M moment will be taken by this joint in this member. But if at this joint there were 2 member or 3 member, means more than one member, and all the members were rigidly jointed, means this joint was rigid joint. For example, the case is like this, means at this joint, this is rigid joint, and 2 members CA and CB are connected here, and I am applying 9 kilonewton meter, means how much will be taken by CA and how much will be taken by CB. And it will be decided by on the basis of their stiffness, means I write stiffness K of CA, means stiffness of CA, it will depend upon far end is fixed, means answer will be 4 EI, EI will be EI divided by L means length 2 meter, so answer will be 2 EI. Now stiffness of CB, KCB. Stiffness of CB can be calculated. Since far end is fixed, again answer will be 4 EI. EI is 4 EI. So 4 EI and divided by L. 4 EI divided by L. Let us suppose answer will be little bit so we can take, if it is hinge joint, if it is hinge, answer will be good like this. If it is hinge joint, we can say that far end is hinge, means answer will be 3 EI divided by L. Answer will be 3 EI divided by L. So 3 will be cancelled like, so it will be 4 EI. Now dear friends, this 9 moment will be distributed in the ratio of their stiffness. I can cut the member at here, and whenever I want to cut, I can cut here and can show like this. This is C, this is C, means one is shear force and other will be bending moment, right? So I want to calculate this 9, it was 9, how much part of 9 will be taken by CA and how much will be taken by CB. So dear friends, it will be taken in the ratio of their stiffness, means for example ratio is 2:4. 2:4 means 1:2. Okay, this ratio is 1:2. How can you divide anything in ratio 1:2? You see like this, 1:2 or 2:4 means add these two, 4 plus 2 6, so one will get 2/6 and other will get 4/6, right? So it will get 2/6 and it will get 4/6. This factor is called as distribution factor, means how moment will be distributed, and it is calculated as the stiffness of this member KCA upon total stiffness, KCA plus KCB, right? So you will say that of this 9, 2/6 will be taken by this member and in the same direction clockwise, so it will take 2/6 of 9 and in the same clock will be applied like this, and it will take 4/6 of 9, so it will be 2/6 and 4/6, so answer will be like 3, this will be 3 and 2 3, this will be 6, right? So answer will be like this. So this member, so I can say that MCA equal to C2A, moment will be 3 and it is since clock, so I will say plus 3, and MCB, it is also clock, I will say this is plus 6. Now if I am applying some moment at joint C, half will be transferred at far end, means MAC will be plus 3/2. Similarly MBC will be 0, because far end is hinge, no moment will be transferred here. So this is the concept of distribution factor. This is the concept of distribution factors. This is the rigid joint. Whenever we want, we can cut the rigid joint and can convert into simple support by applying fixed end. For example, let us take, this is the case. So what will be, for example, this type of questions are generally asked. This is hinge support, let us take, this is fixed support, and this is free and it is hinge support. This is E, this is A, this is B, this is C, and this is D. This is, let us suppose 2 meter and its EI is EI, and it is 3 meter and its EI is again EI. It is 2 meter, its EI is 2 EI, let us suppose, and it is 3 meter and its EI is 2 EI. For example, dear friends, he asks you, this is O is rigid joint and I am applying 18 kilonewton meter moment at O joint. Calculate the moment distributed in all members and also calculate fixed end moment MAO, MEO like that. So how will we calculate? Dear friends, you are applying 18 kilonewton at a joint which is rigid, means this 18 will be distributed in all members, and some moment will be given by MOB, means moment in member OB from O to B. Some will be given in OA, some will be in OE, OD and OC. So how we solve? Listen, there is a procedure, means if you solve this in exam, so you should follow this. Joint is 1, this is the joint is O. How many members? Members are OA, OB, OC, OD, OE. Stiffness, you can calculate K of each member. See, this is OA. Stiffness of OA means far end is fixed, so stiffness will be K equal to 4 into EI is EI divide by 2 means 2 EI. OB, far end is hinge, and answer will be 3 EI divide by 3, answer will be EI. Far end is fixed, OC, so it will be 4 into 2 EI, 4 EI divided by L, so it will be 4 EI. OD, since OD cannot take any moment, it is the end free, it will rotate straight like this, so it cannot take any moment, so stiffness will be 0. If far end is free, so stiffness will be 0. And OE, in OE it will be 3, EI will be 2 EI and divide by L will be 3, so answer will be 2 EI, right? So now you will calculate summation K, total stiffness, 2, 3 and 4, 7 and 2, 9, it will be 9 EI. Now you will calculate DF, distribution factor, means the moment will be given in this ratio. And how will calculate ratio? Add these all. One will get 2 upon 9, other will get 1 upon 9, other will get 4 upon 9. So this is called distribution factor, and it is given as K upon summation K, means 2 EI upon 9 EI, it will be 2 by 9. It will be EI upon 9 EI, means 1 upon 9. It will be 4 upon 9, 0, and it will be 2 upon 9. Means if we want to calculate moment, means MOA, O to A, I will say MO to A will be 2 by 9 of 18. 2 by 9 of 18 means 4. It will be 4. Now if I want to calculate, and see, this is MOA. If I want to calculate MAO, if I am applying 4, so half will be transferred here, so MAO will be half. Now if I want to calculate MOB will be 1 by 9 of 18 means 2, and MBO will be 0 because far end is hinge. Now MOC will be 4 by 9 upon 18, it will be 8, and MCO will be half, means 4, because far end is fixed, MCO will be 4. Now MOD is 0 and DO will also be 0. This is free end, it will not bend, means bending moment will be 0. Now similarly MOE will be 2 by 9 of 18 means 4, and MEO will be 0. So he will ask you these, means calculate MAO, or he can say that calculate end moments at A, B, C, D, E. So these are the end moments, and these are MOA, means moment at this joint A. So let us continue. See, he can also ask you that also calculate slope of joint O. Slope of joint O, how can you calculate joint? I asked you, whenever you want, you can break this as like this. this is rigid joint. You can make whenever you want, make hinge joint and apply moment. A fixed joint, whenever you want, you can convert a fixed joint into hinge joint by applying the moment applied at this joint. For example, this is a fixed beam, this is a fixed beam, loading is there. I say that reactions will be, one will be this, other will be this, and other will be this, one will be this, other will be